Let me just get started with a little bit of motivation. So here's like a map it's one way of characterizing different superconductors. It's called the UMRA plot. There are different implications of this plot, but I'm not going to go into that implication today. I just want to use it as a motivation where we can look at this y-axis, which is the critical temperature of the superconductor. And this x-axis is actually a Fermi temperature, but you can kind of simply think of it as something that's proportional to the electron density in your material. So very crudely speaking, this sort of tells you, based on how many potential workers you have in your system, what is your output efficiency. So if you look at this lower right region with relatively higher electron density and low TC, there is a group of materials called weakly coupled BCS superconductors like aluminum. And now if you try to go to the upper left corner, there is a bunch of materials that falls into this band region that has relatively lower electron density and higher TC in comparison to the weakly coupled BCS superconductors. So these superconductors are generally driven by mechanisms that are far stronger than these weakly coupled superconductors. So they are called strongly coupled superconductors. And many of these materials are also driven by strong electronic correlations as well. And now if you look at this region with relatively even lower electron density, this is sort of empty, right? So being able to make materials in this region with low density and relatively higher TC would be of both fundamental interest and good for technological applications. So here's a little bit of brief motivation for the talk today. And this is an outline of what I'm going to talk about today. So assuming that not everyone is from our moire to the twisted field, and also assuming that most of you guys are theorists, I just want to give you a brief experimental context on using two-dimensional twisted materials to study correlated physics and superconductivity with an example of something called magic angle twisted bilayer graphene. And I'll move on to the main parts of my talk, which will be on magic angle twisted trilayer graphene, and then establishing a whole magic family of these twisted graphene structures. Okay, so the first part. So the conventional way to study a lot of this strongly correlated physics and unconventional superconductivity and so on has been to chemically synthesize these materials. And as you will all agree, when we try to study this, one major degree of freedom that we want to be able to control is the number of electrons in the system, which is called doping, right? That's because depending on the number of the electrons in the system, the modes of the interactions between those electrons will change, and that will lead to different kind of phenomena in the structures. And as you can see in this famous phase diagram of copper oxide, being able to tune this doping concentration and with another variable and obtaining this entire phase diagram is very important for having underlying physics in the system. But experimentally, what this means is that for every single point on this x-axis, you need to make different materials while varying the ratio of the different chemical components in your system here. So on the little bit more tunable side, we have something called cold atom systems, where you're basically making artificial lattice potentials made out of laser beams to try to mimic the crystal lattice. And you can simulate similar types of strongly correlated physics as we're seeing in the real material systems, but while having the in situ doping tunability. So the question is, can we achieve this sort of in situ doping tunability, but then in real materials? So in that context, a very good candidate is two-dimensional materials, which are the atomically thin counterparts of the three-dimensional materials. And that's because now the doping process becomes so much easier because you can just put this nearby metallic gate and try to apply some voltage across your two-dimensional system and your metallic gate. And now the charges would start accumulating on the surface, and that's going to control your doping through this electrostatic process. And as you can see in this example of graphene Dirac cone, you can basically tune the chemical potential of your system while applying the gate voltage across your 2D material and the metallic gate. So I'm just showing you because there is a little bit of subtle implication of using this electrostatic doping in terms of interpreting some of our experimental data later on. And further advantages come from the fact that we can stack any number of two-dimensional layers on top of each other to create composite structure. And I mean, there are subtleties in terms of fabrication of these structures, but still if you put those layers together, they are going to be put because you're literally mechanically putting them on top of each other using your hand in some sense. So you're not limited by the thermodynamic stability of the chemical synthesis in this sense. And we have even further degree of freedom, which comes from the relative twist angle between the two layers. So we have a hexagonal lattice, such as in graphene, and then you can put another layer of graphene on top of that existing hexagonal lattice and start twisting them. And you can see this new pattern arising that's longer length scale. This is called the Moiré pattern. Okay, so why do we care about whatever this Moiré pattern? And that's because this Moiré pattern allows us to design and modify the band structures in our system. So as you can see in this example of two layers of graphene twisted on top of each other, you have two graphene Dirac cones, and then if they're twisted at a small twist angle, the Dirac cones start hybridizing, and there is a point at which, this is called the magic angle for graphene of the twist angle of around 1.1 degrees, where the bands near the zero energy become almost completely flat, as you can see in this energy momentum dispersion. So basically, you can achieve this flat band engineering just through twisting two layers of graphene, which are not necessarily strongly correlated materials. And in these flat bands where interactions start dominating, people have found superconductivity in the system, as you can see in this map of resistance as a function of temperature, and the x-axis is the charge carrier density, which is the doping control. So you can see these two superconducting domes that are surrounding this so-called correlated insulator states in this material. But what I want to emphasize here is if you look at the scale of the x-axis, which is the charge carrier density in the system, this is an order of magnitude smaller than the other superconductors that we have seen in the OMRAP plot. And the fact that you can observe superconductivity at finite temperature or observable temperature in the lab in such low density makes it a very strongly coupled low density superconductor. And in these materials, although I'm not going to go into any of the details today, here's a brief schematic of different phases that were found in magic angle twisted bilayer graphene. As a function of this x-axis is again the charge density in the system, and the temperature and magnetic field. We have found superconductivity, insulator states, metallic states, some topological phases. And even, I guess, more surprisingly in some sense, we have also found magnetic phases in this all carbon-based material that don't have any magnetic ions in the system. So we can see that it's a nice platform to study correlation topology, superconductivity, and so on in a single sample. So since the discovery of this magic angle twisted bilayer graphene 6 years ago, people have found other kinds of correlated topological, magnetic, and even ferroelectric phases using this Moiré structure engineering. But one very interesting thing is that, at least for the first several years, robust and reproducible superconductivity was found only in magic angle twisted bilayer graphene, even though some of these other systems also have very flat bands. So that leads us to the question of what really drives this robust superconductivity in magic angle twisted bilayer graphene. And having just a single material or a single system, it's hard to really understand the origin of it. And we also, as I showed you in the previous slide, we have a motivation for finding more systems in this low density, high TC, strongly coupled superconducting region. So the questions at the time were can we design or find a tunable or even better strongly coupled superconductor using this Moiré engineering? And if so, can we actually find some more general important ingredients or recipes for forming such kind of robust superconductivity? Is the symmetry of the system, whatever that is that the important thing? Or the details of the band structure, is that important? So there goes the first main part of my talk today, which is going to be on magic angle twisted trilayer graphene. So here's the structure. Now we have 3 layers of graphene, where the adjacent layers are twisted by theta and minus theta, so that the very top and the very bottom layers are basically aligned, and the middle layer is at a relative twist angle. And in this system, we have an additional mirror symmetry plane in this structure, in addition to the C2T symmetry that was present in the magic angle twisted bilayer graphene. So this twisted trilayer graphene structure that's twisted in this alternating twisted fashion is like one of the very few systems that actually preserve the C2T symmetry of graphene. And I call this magic angle twisted trilayer graphene. Why is this magic, and why did we choose this system to answer the previous questions? You will see the answers in the next few slides. So how do we understand this kind of trilayer system? So in general, if you twist 3 layers of graphene, or like just more than 2 layers of graphene, calculating the band structure actually becomes kind of much more complicated, because you have now 2 interfaces that can induce Moiré potential. And if you have 2 different Moiré potentials, that can lead to even longer scale Moiré length scale that's called super Moiré. So that kind of becomes a complicated problem. But in this specific case of this alternatingly twisted trilayer graphene, the problem becomes much simpler, because you only have a single periodicity, because the twist angle between the first one and then the second one are exactly the opposite. So it turns out that you can actually block diagonalize this twisted trilayer graphene Hamiltonian into a form where you have this magic angle twisted bilayer graphene-like block and a separate monolayer graphene-like block. So that means that we can decompose this twisted trilayer graphene structure into a combination of twisted bilayer graphene, but then the square root of 2 enhanced interlayer tunneling factor plus a separate monolayer graphene. And I just want to emphasize that these 2 twisted bilayer graphenes, it's not corresponding to any of the physical layers of this twisted trilayer graphene. It's a superposition state of different layers. So if you just put a magic angle twisted bilayer graphene and on top of it some random monolayer graphene, you're not going to achieve the same band structure. Okay, so because we have this square root of 2 larger interlayer tunneling factor, our magic angle for twisted trilayer graphene becomes exactly square root of 2 larger than the magic angle twisted bilayer graphene magic angle, which would lead us to 1.56 degrees instead of 1.1 degrees. And shown here is a band structure for this twisted trilayer graphene structure, where you have this orange flat band that looks exactly like the magic angle twisted bilayer graphene-like band, and you have a separate monolayer graphene-like Dirac band that's existing in the background as promised. And I just want to emphasize that the C2T symmetry of the system is what protects all of the Dirac points in these band structures, and the mirror symmetry that's present in the system is what allows this block diagonalization so the separation between the magic angle twisted bilayer graphene band and the monolayer graphene band that's separated by the mirror symmetry of the system. Okay, so we have experimentally realized this system and found robust superconductivity with a TC of around 3 Kelvin, which is, I think, still the highest in, I guess, our 2-dimensional Moiré community. And we can also see the sharply switching VI curves, which basically shows you that it's a true 2-dimensional superconductor. And when we apply some small magnetic field, we see this oscillatory pattern that's called the Fraunhofer pattern, again, also showing you that this is a real true superconductor. So we have already found a low-density robust Moiré superconductor by making this magic angle twisted trilayer graphene. So that's cool, but is that it? It's not that fun, right, if that's it. So it turns out that this trilayer graphene gives you so much more than twisted bilayer graphene, because if you look at this band structure, I told you that the Dirac band and the flat band are separated, sort of protected by the mirror symmetry of the system. But now if you start breaking that mirror symmetry by applying the electric displacement field to the system, you start hybridizing those 2 bands. So you can basically tune the band structure in situ and the interactions in situ by applying the gate voltage. So how do we do this experimentally? So instead of having just a single gating layer, we have now 2 gates, one on top and one on the bottom. And you can see in these schematics that you can tune the charge density and the displacement field independently by changing the signs of the relative voltages that we're applying to the top and bottom gates. So just for fun, it's a real image of microscope image of the device that we usually fabricate. So this part is the bottom gate, and then these yellow parts are the top gates. So we have the dual gates, and our actual twisted trilayer graphene structure is sandwiched between these two gates. And these are the electrical contacts that we put to measure the transport properties. Okay. So we can just get into the data directly. So here's the full phase space map of resistance as a function of the x-axis is the usual charge carrier density, and the y-axis is the electric displacement field as I promised. So I just want to emphasize that in the case of twisted bilayer graphene, it would be sort of this one line here at zero displacement field when you try to measure that. But now we have gained this entire y-axis in the system due to the presence of the extra Dirac band and the hybridization between the two bands. And before going into any of the details, I just want to go over what this x-axis means. Because I put this as like this nu, which is equal to 4n over ns. Like, what does this mean? It ranges from 0 to plus minus 4. So what does this scale mean? So when we achieve this kind of new mini Brillouin zone by twisting 2 layers, 3 layers, or whatever, 4 layers of graphene, whatever number of layers of graphene, you still have this twofold spin degree of freedom and twofold Valley degree of freedom that comes from just like in a monolayer graphene. So in total, you still have 4-fold spin and Valley, isospin or flavor degeneracy in the system. So that means basically you require 4 electrons or 4 holes per the new Morey unit cell to fill each of the flat band in either direction. So you need 4 electrons to fill the positive flat band. You need 4 holes to fill the negative flat band. So if we come back to this diagram, what this means is that this 0, nu equal to 0, is corresponding to the charge neutral point in the band structure. And as we tune to the positive side, plus 4, that's basically fully filling the flat band that's in the positive energy. To the minus 4, that means you're fully filling the flat band in the negative direction, in the negative energy. And 1, 2, 3, 4, they're basically the number of charge carriers in your system. 1 electron per Morey unit cell, 2 electron per Morey unit cell, and so on. So there's a lot of features that are going on in this phase map, which I'm not going to go into any of the details of these different features. You can refer to the paper. But I want to emphasize, this blue region of zero resistance, which is basically the superconducting regions. And you can already see that they're highly dependent on both the charge carrier density or the filling factor and the displacement field. Okay? And we can also see that when we try to extract the TBKT, which is the TC for two-dimensional superconductors, you can see even the TC has a very large dependence on both the charge carrier density and the displacement field. So we have achieved a very tunable system where we can tune the superconducting strength throughout the entire phase map in a single device, in a single cool down. So now we want to understand what's actually going on underlying under this structure. So in order to do that, we measure something called the hole density. So this is the map of the hole density in the same exact phase space. But I also want to provide an experimental context of why we want to measure something called the hole density in the system. So when we try to dope the system in this x-axis, as I showed you, we're basically applying the gate voltage to the system. And that's what we intend to dope. Like, it's not like really you're changing the actual number of the electrons in the system monotonically, but that's what we want the system to be in, right? So that's just an experimental subtlety. But so if your band structure is a super simple, just single particle band structure that just doesn't change at all as you try to dope the system, it doesn't matter. That's exactly how many electrons you're going to put into the system. But that's really not the case of our system, and that's the whole point of studying the strongly correlated materials and unconventional blah, 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 right? Because you want to change, there's many phase transitions that change the band structures or the interactions when you try to put different numbers of electrons to the system. So that's what we want to figure out by measuring this hole density. So hole density basically tells you the type of carrier that you have in the system. Is it an electron-like carrier or the hole-like carrier? So by measuring such quantity as a function of this intended doping in some sense, we can see what's going on in your Fermi surface topology. So let me just point you to some of the key features in the hole density as examples. So here's this feature called gap or Dirac-like behavior, where your hole density, this is the y-axis, which is the color scale, basically linearly crosses 0 and changes sign as you change the intended doping of the system. So for example, you just switch from hole-like carrier to the electron-like carrier or vice versa. And that basically corresponds to a simple gap or Dirac point, which makes sense, right? And that kind of behavior is happening at the actual charge neutral point, which is supposed to be a Dirac point, and some of the other features here in these integer filling factors. And another feature that we can pay attention to is called this resetting feature, where your hole density was increasing, but then it all of a sudden drops to 0, and then it starts refilling. So it resets to the 0 density in some sense. And that kind of resetting feature is happening at low displacement field integer filling factors, as you can see in these regions. And the third type is this thing called Van Hoff singularity, where your hole density was increasing and then abruptly it changes sign by diverging, and then it comes back down to 0. So this is like a saddle point behavior, and you can see this Van Hoff singularity-like feature in the higher displacement field areas like here. Okay, so now we can try to put the two maps side by side. And just even visually looking at it without any further data analysis, you can see that there are striking similarities between the features of the resistance and the hole density. So especially notable is the superconducting region boundary shapes and some of the features in the hole density, right? And in order to compare this better, we can put those features in a single map. So shown here is the same exact face map, but with the key features in the superconductivity that's shown in this light blue region, and the hole density features in these color-coded lines. So you can basically find that the superconducting regions are basically very well bounded by both this blue Van Hoff singularity and this yellow resetting features. And just for double checking, in case you're wondering, like can we really trust all this hole density data, we can double check by taking some line cut across this line across the Van Hoff singularity and try to measure the effective mass of the system. And you can see that along this line, the effective mass basically diverges at this exact point. And this exact point is exactly where your TC of the system drops to 0 and your resistance becomes non-zero. So the Van Hoff singularity is really bounding your superconducting boundaries, and this is the case throughout the entire phase map.
The effective mass is measured in quantum oscillation?
Yes. Yeah, so we can say that the superconducting regions are bounded by the Van Hoff singularities, and in some sense this is exactly the opposite of what you would expect for a weakly coupled BCS type superconductor, where the TC of the system is supposed to be the maximum, not the minimum, at the highest density of state in the system. So now we want to understand, what's really forming the superconductivity, what's the underlying electronic structure. So now we can come back to the fact that I told you there was fourfold isospin or flavor degeneracy of the system that were giving rise to this scale of 0 to plus minus 4, right? So we want to ask the question, as we start doping the system into the flat band, are we really filling all 4 degenerate states together? And if that's the case, it really kind of doesn't make sense, right? If that's the case, like why do you see all the very different features at the integer filling factors, and why is superconductivity happening only at certain regions, right? So we want to study whether there's a symmetry breaking of this flavor degeneracy. And we can do this by basically taking some quantum oscillations across this density line, or any density lines in this entire phase map. And here's the data of what you can find. So I mean, it's kind of complicated with the color scales and stuff, but basically the whole point is that by tracking the sequence of these Landau fans, we can see the current symmetry of the system that are present in the integer filling factors. And when we perform that analysis, we can see that there is a spontaneous breaking of the flavor degeneracy at the integer filling factors, which means that the electronic structures across the different filling factors are not exactly the same.
So do you have an understanding of why you see nothing at -1?
I do not have an understanding. So I think it's also, it's an interesting question that many of both experimentalists and theorists are wondering, why is there in general the electron hole asymmetry in all these magic angle twisted graphene structures? Some people believe there is this subtle difference in the band structure flatness that might induce that. Some other people believe there are some other things, but yeah, basically, yeah, answer is I don't know, and I don't think it's clear yet. And yeah, and just to confirm that, like, just to show you that we're not the only ones measuring this symmetry breaking, we can also directly measure the chemical potential of the system as a function of doping. And we can see that there is this, pinning of the chemical potential at each integer filling factor that's also induced by the exact same symmetry breaking of the flavor degeneracy. So now, using the same kind of quantum oscillation data, we can also assign the dominant filling factors or the charge carriers for each region in this phase space. So we can see that these regions are dominated by the carriers that are emanating from the nu equal to ±2, and then these other regions are from different integer filling factors. And you can already see from this data that it's only in this ±2 region where the superconductivity is present. But only from this single line, you might think that, oh, it might be just some coincidence, right? Like, it doesn't really mean that the ±2 carriers are necessarily related to the superconductivity. But now it becomes helpful that we have this entire y-axis, because we can perform the same analysis throughout the entire y-axis line cuts. And for example, if we take a line cut of quantum oscillations across this line at high displacement field, where we have extra superconducting domes, it's very surprising that we can actually find extra Landau fans that are actually emanating inward direction from the nu equal to 2. So that inward fan was not present in the low displacement field region. And now, as soon as this inward fan becomes available, you have the superconducting regions appearing. And this is not, again, this is not a coincidence. At certain line cuts, we can see the exact continuous behavior of the Landau fans starting appearing from this region, and that's exactly where you start seeing the extra domes of superconductivity in different regions. So we can say that the superconductivity is probably very intimately related to the same symmetry broken carriers from the half filling. Okay. Yeah, so we saw that there's this superconductivity that's not really weakly coupled, and it's emanating from the half filling carriers. But we can also show you that the superconductivity is not just not weakly coupled, but it's actually very strongly coupled. So we can first measure this Ginzburg-Landau coherence length, which is shown in this pink plot, and compare it to the average inner particle distance. So this average inner particle distance is actually calculated from our Landau fans, and it's not some random value. So this is actually the estimated inner particle distance in this particular device, and we can compare that value to the coherence length, and you can see that they're in the very similar scale of the Moiré length. So that really tells us that our Cooper pair size is probably at most the average inner particle distance, which makes it a strongly coupled superconductor. And we can have another type of measurement where we can get the ratio between the Tc over the Fermi temperature, and this ratio is going above 0.1, which also tells you that it's likely to be very strongly coupled, possibly near the BCS-BC crossover regime, although this exact statement might be of question to some of you. But we can for sure say that it's a very low density superconductor, which has very strong coupling between the Cooper pairs. And if we come back to this UMRA plot, we can try to place our system in this map, which puts it here. One of the very strongly coupled superconductors in this low density regime. And just to give you some experimental context of why we would care about this kind of ratio at all is because our system, the TC is not that high, especially compared to the high TC superconductors. It's like 3 Kelvin. But actually, given the number of such low density in our system, that number of 3 Kelvin TC is considered actually very high. So if we can understand the pairing mechanism of our system, it might provide some important insights into designing future materials with actually higher TC. Okay, so we saw that our superconductivity is pretty unusual in different senses. And can we learn a little bit more about the underlying structure of the superconductivity? So we all know that the superconducting wave function consists of 2 parts. The spatial part, which can be S wave, P wave, D wave, and etc., or some complicated versions of these, and the spin structure that can be singlet, triplet, or also the mixture of singlet and triplet, and so on. So for a very simple BCS type spin singlet superconductor, where the gap can be estimated by the TC through this relation, when you try to apply the Zeeman field to break the singlet-Cooper pair, you're going to kill your superconductivity because you literally just kill the Cooper pairs. So there is this something called the Pauli limit, which basically provides you an estimated critical magnetic field at which your superconductivity will be sort of suppressed based on your TC of the system. So this means that for a BCS spin singlet superconductor with a TC of around 1 Kelvin, a Zeeman field of around 1.86 Tesla will likely to suppress the superconductivity. So it just gives you some sort of scale in your head to compare it to. So we can measure our critical magnetic field with the Zeeman field in our system and try to compare it to the nominal Pauli limit. So how we do this experimentally is because here's our device structure where our twisted trilayer graphene is in this plane with the gates and the electrical contacts, and we can try to apply the magnetic field in the parallel direction as the twisted trilayer graphene in the 2D plane. So that's how we hope to induce some Zeeman field in the system. So now if we look at the results, we can see that our critical magnetic field in the system exceeds the nominal Pauli limit that we can estimate from our TC by around 3 times. Okay, and I want to emphasize that that Pauli limit violation is consistently the case throughout the entire dome. So this is the entire superconducting dome. So it doesn't have that much dependence in some sense. It's consistently violating. So this sort of rules out the fact that some of you who are more familiar into the strongly coupled superconductivity, you might think that, oh, if your Cooper pairs are strongly coupled, that means you will have this sort of pseudo gap, or your gap will be much larger than the TC, so you're not estimating the exact Pauli limit correctly. But if that's the case, you should see some sort of dependence across your superconducting dome, because our coupling strength drastically changes across the dome, as we already saw in the Ginzburg-Landau coherence length plot. Okay. And this is interesting, especially when compared to magic angle twisted bilayer graphene, whose critical magnetic field was sort of following the nominal Pauli limit pretty well. And now if we tune to a different point in this phase space, we can see something that's even more striking. So once we kill the first dome of superconductivity at around 8 Tesla in plane field, if you apply even higher in plane field, you actually start seeing this new dome of superconductivity. So this sort of reentrant superconductivity at higher magnetic field, sort of also in combination with the Pauli limit violation, tells you that the spin structure of the magic angle twisted trilayer graphene is pretty unlikely to be a simple spin singlet. So I won't say it's spin triplet or anything. It could be many different things, but it's unlikely that it's a simple spin singlet structure based on these evidences. And you can also tune the reentrant superconductivity as a function of both the displacement field and the doping with our in situ tunability of both parameters. And more recently, just as a quick note, not going to go into the details, but we've looked at the magic angle twisted trilayer graphene system a little bit more closely with precise local probes. And we find that actually we were sort of ignoring the presence of this Dirac band at zero displacement field, right? We were sort of only considering the flat band, what's going on in the flat band, and so on. But we can actually see some evidence that the Dirac band is actually quite occupied the whole time at the integer filling factors. So that might be also playing some sort of physics. We don't know what, but we saw some, evidence that they're always occupied as well, in addition to the flat bands. So we can't really just ignore that completely. Another little thing that we also found recently is that in an ideal case, our structure is mirror symmetric, right? Because we were intending to put the top and bottom twist angles as exactly the same, but in opposite directions. But in reality, there is a chance that they're not exactly the same. So in transport features, it was homogeneous enough for us to ignore because we were seeing exactly the same features in the positive and negative displacement fields. But when we use precise local scale probes, we can find that this sort of difference in the twist angles between the first two layers and the second two layers that induces a larger scale supermoire pattern. And we can even see that even at that supermoire scale, the flavor symmetry is broken. So you can see, in addition to the original flavor symmetry breaking at the half filling in the flat band as shown in this gray fans. In addition to that, we have an extra fan that's next to it that's shown in this blue, which is coming from this larger supermoire scale filling. Okay, so we've seen that there's this one other tunable system, magic angle twisted trilayer graphene. Is that the end of the story? Also, obviously not, because it turns out that we can actually have the whole hierarchy of this magic angle structures as long as your structure has this alternatingly twisted theta minus theta, theta minus theta, and so on structures. And that's because if you still keep that single periodicity, as was seen in the twisted trilayer graphene slide, we can basically keep block diagonalizing the entire Hamiltonian, where you can basically make one of the block of TPG to be a magic angle-like flat band block, and rest of them will be some random other band structures that are lying in the background. And I want to emphasize that this entire magic family structure shares this same flat band of block diagonalizing or making this first block magic angle. And then you're also keeping the C to T symmetry of the system. And you can see in the band structure calculations for the 2-layer, 3, 4, and 5 layers that they indeed all share this same flat band in the system while having different bands in the background, depending on the number of the layer structures. And just as was done in twisted trilayer graphene, you can also apply the displacement field to induce the hybridization between the other bands in the background with the flat band and see how those interactions lead to different phenomena. And we have experimentally realized the structures up to 5 layers, and you can see the resistivity as a function of temperature for magic angle twisted bilayer graphene, twisted trilayer, 4-layer, and 5-layer, and you can see that they're all very superconducting. So we can say that we have established a whole family of strongly coupled low-density superconductors through this mechanism. And just also briefly, I just want to tell you that I made around 10 devices of 4- and 5-layer structures around the time of the first paper, and it's basically 100% magic, and we can always get the superconductivity in all of the structures. So I just want to emphasize that it's not like we can make 100 devices and maybe 2 of them superconduct. It's a very robust family of superconductors where you can study different physics that are appearing consistently.
We saw an increase in the TC went from the 5-layer to the 4-layer. Is it also the case when you are increasing the layers? Is there a relation of it with the TC, or does the TC more or less remain constant?
Yeah, so that's a good question. So I wouldn't necessarily say that the TC increases between 2 to 3 or 3 to 4 or anything. That's basically sort of unknown. So different samples have slightly different twist angles. So it's not like I can make, well, 10 devices or 20 devices, but we might not be hitting the exact optimal magic angle point for each of the layers. So it's a little bit hard to quantitatively compare the TC between the different layer structures, but based on my experience, I think all of them, for the best devices around the optimal magic angle, they're all sort of around TC 50% of maybe 3 Kelvin or so, yeah.
Does the moire unit cell get bigger as you stack more layers?
It gets smaller because as you saw in the twisted tri-layer, if you remember, the block diagonalization makes the interlayer hopping actually increase by its square root of 2. So in order to obtain the same kind of flat band, you have to make the angle actually larger. Yeah, and then if you make the angle larger, it means that the unit cell is going to be smaller. I don't know, yeah.
Can you gate all the layers, or are you still doing like a top and bottom layer?
That's a very good question. So I have a separate slide later on, but that I can show you later. But basically, it is a little bit difficult to gate all of the layers consistently if we have, basically beyond 3 layers. I think it's difficult. So that leads to different consequences. For example, if you look at this map this is for 5 layer, you can see that the superconducting dome actually extends this, plus minus 4. But I don't think that means that it actually extends beyond the flat band. It probably has something to do with the gating mechanism that we have. And another thing that I want to comment on that aspect, and then the other aspect that the other person just asked about the superconducting TC, I also kind of wonder if the fact that we don't see any increased TC in the larger layer structures where people were actually expecting to see a little bit higher TC, the fact that we don't see it, I wonder if it might be related to the issue that you just mentioned. We're not really gating all of the layers simultaneously. And for example, in the case of twisted 5-layer structure, I think when the theorists calculated the wave function, it's sort of the flat band wave function is concentrated in the very middle layer. And we can't basically gate that middle layer because of screening. So I also am curious if that leads to, yeah.
Just to make sure I understand the experimental complexities with gating these structures. In principle, if you could separately contact each layer, you could make sure the displacement field is uniform across the system, but what you're challenged by now is that you're only gating the top and bottom of the 5 layers?
Yeah, so the gating is actually not through directly putting the voltage on your system. It's more like you have separate metallic gate. Yeah, so we're keeping all of our system to be measured at 0 voltage, like 0 DC voltage, and we're using the AC to measure the resistance. And we could, of course, also apply some gate to the middle structure, but I'm not sure if you can separately gate this layer different than this, because they're all in some sense shorted. They're all graphene, they're conducting. So yeah, I think there is a little bit of technical difficulty. Yeah.
One question, purely technical one. So in twisted 5-layer graphene, we have well isolated bands, so we know where we have band gaps, and we can assign density just to the narrow region. In other systems, the bands are strictly speaking not being gapped. So for TTG, I guess we can see the dip, the maximal resistivity, and we can assign then again density. But for more and more layers, we have more and more dispersive bands. So I guess this feature becomes less and less pronounced. So how certain we are of densities here?
Yeah, that's a very good question. So just to make sure, the way at least our lab assigns this density is not just through the map of the features. We are doing it through the quantum oscillation Landau fans to make sure that that point is actually where the end of the carriers emerge. So that's how we assign it in the first place. So that method in general still works for all of the layers. But the point that you mentioned, which is probably related to the fact that you're probably also filling the other bands simultaneously, right? So that's also another point that I showed you briefly with the recent twisted tri-layer experiment, that they are present. So I would say that assigning the super lattice, it's still okay. I don't see many features. Still, somehow the super lattice is it's just emanating to a single point. So I think that's okay. But whether, how accurate this 2, 3, 4 exactly by dividing that region into 4, that might have a little bit more trickiness because already in twisted trilayer, the region where the Landau fan from the half filling factor, where that goes, it's not exactly half of where the nu equal to plus minus 4 goes. So you have a good point. I think it was small enough, at least in 3 layers, that we could sort of ignore for the major features, but it is a present effect in the larger, yeah.
On the previous slide, should I be reading into like the fact that the high temperature resistivity is dropping like dramatically here? Anything interesting, or is that just like very easily explained?
Oh yeah, so that's a good point. So that's related to what he just mentioned. There are other bands present in the background. So basically you're sort of shorting. You're never really in the full band gap. Those Dirac bands and other twisted bilayer graphene-like bands in the larger layer number structures are always present. So you can always conduct through those channels, even if your flat band itself is gapped. Yeah. Okay. Yeah, so we have this family of superconductors from 2 layers to 5 layers. Are there, can we study a little bit more if they have any differences? So naively, just looking at the physical structures, you might think that, the odd layer number of structures have the mirror symmetry and the even layer numbers don't have that global mirror symmetry. Maybe if there's any difference, could it be between the even number layer structures or odd number layer structures? So let's see if that's the case or if there's any difference in general. So we can first perform this magnetic field experiment where we can compare our critical magnetic field to the Pauli limit as we did for the twisted trilayer. And we already saw that twisted bilayer graphene is not really violating the nominal Pauli limit, but it turns out that all 3, 4, and 5 layers consistently violate the Pauli limit.
So for twisted bilayer graphene, was it not the case that there was that the magnetic field was causing some orbital, coupling to the orbital degree, so the Pauli limit measurement was not very valid, right? But trilayer solved that problem to some extent because it did not change the orbital degree, couple to the orbital degree. So is it meaningful to talk about, not Pauli limit violation in twisted bilayer?
Oh, so that's exactly the point. I mean, we did the experiments, this already kind of 2 years ago, so it's sort of before all that interpretation came to mind. So that was actually the whole point that I'm going to mention. I think you're already knowing a little bit too much, I think. Yeah. Yeah, so this is the experimental observation, and I'll explain that again later on. And then we can also look at the in-plane magnetic field response, but with this angle dependence. So instead of just applying the in-plane magnetic field into some random single direction in the in-plane, we can also have our vector magnet and change the in-plane field 360 degrees around this entire 2-dimensional plane and see if that causes any anisotropy in the system. So it's a separate work, but for twisted bilayer graphene, I can just explain this plot. So this plot is a resistance map as a function of this in-plane magnetic field in this 360 degrees direction that I just told you. And we can see that the zero resistance region of superconductivity, shown in purple, transitions into the orange region of finite resistance as we apply the in-plane magnetic field in different directions. And as evident just already visually, you can see that this shape of the critical magnetic field is it's elliptical. It's not isotropic. So there is some sort of anisotropy in the system where Rafael and others have interpreted as the nematicity in the twisted bilayer graphene. But for 3, 4, and 5 layers, we don't see such elliptical behavior. We don't see any anisotropy, and it's pretty isotropic. And I just want to mention that these are not plots at some very specific points in very specific samples. We have measured basically for all the samples that we have fabricated and measured, we have done these exact same measurements, and they're consistently the case where the 3, 4, and 5 layers don't show the anisotropy, and the twisted bilayer graphene always shows this elliptical anisotropic behavior. So now if we just try to summarize the results, We can see that the correlated insulator and superconductivity features are what's shared among all of the family members, whereas the magnetic field response, there is a difference between the twisted bilayer graphene and the higher number layer structures, where the twisted bilayer graphene didn't really violate the Pauli limit nominally, but there was this nematic or anisotropic in-plane magnetic field response in the superconducting region. So how do we understand this issue, the difference between the 2 and 3, 4, 5 layers? So as mentioned by one of the people in the audience, it turns out that we could actually understand it in a pretty simple picture of this something called in-plane orbital effect. So when we were applying the in-plane magnetic field to the system intending to purely induce some Zeeman field, the side thing that was happening along was that there is this extra flux that's penetrating sideways because the electrons hopping between the adjacent layers gain extra phase through this magnetic field. And you can see that that effect would be just most prominent if you only have 2 layers, but if you have 3, 4, 5 layers, actually the fluxes cancel because they have opposite signs. And we can also see this effect in this simulation of the Fermi surface for the twisted bilayer graphene. This is the Fermi surface in the presence of some magnitude of in-plane magnetic field. We can see that there is the deformation of the Fermi surface. And we know that that leads to the suppression of the superconductivity in general. And that also induces some sort of anisotropic coupling to the system, which we think lies behind the observed nematicity. But for 3, 4, and 5 layers, your Fermi surface basically remain almost exactly the same, even in the presence of the in-plane magnetic field, because those fluxes just canceled with each other. So you can also simulate this orbital G factor that's sort of an analogous quantity as the spin G factor as in the Zeeman effect, but then it's in for the orbital effect. And you can see that the multi-layer structures have just very low orbital G factor compared to the twisted bilayer graphene, even in the absence and presence of the displacement field where you break the mirror symmetry. So this sort of explains the observed differences among the different structures and in the experiments. So the whole point I just wanted to mention once more in terms of this nematicity. So the absence of the anisotropy in the 3, 4, and 5 layers, it doesn't really mean that there is the superconducting phase is somehow different than the twisted bilayer graphene. It's more like the question of, can we use the in-plane magnetic field as a probe to probe something that has broken rotational symmetry in the system? Because experimentally, in order to probe that with this in-plane magnetic field, you need to have some mechanism to couple to whatever symmetry in the system. But if then that coupling is done through the in-plane orbital effect, so if you don't have that coupling present in the system, you can't really probe. So that's the whole point. It's not like some system has nematicity, the other don't. Okay, so now if we come back to the original questions that I was trying to ask in the beginning of my PhD, can we design a new tunable, strongly coupled superconductor? The answer is yes. We found this system that actually goes beyond twisted bilayer graphene with exceptional tunability and interesting aspects of superconductivity in the system. And can we find some important ingredients or recipes for forming this kind of robust Moiré superconductivity? The answer is also yes, because we have established the whole family of these Moiré superconductors through this mechanism that share the same flat band and the C2T symmetry of the system. The questions that still remain in the field for a while now is trying to figure out the exact superconducting order parameter of the system, which has a little bit of experimental difficulty. And along with that, what is exactly the microscopic mechanism that leads to whatever order parameter that's present in the system? And the ultimate question in the engineering point of view would be, how can we increase the TC further using our understanding from these magic angle structures? And one more aspect that I want to mention today is that there's a bunch of Moiré systems with all kinds of correlated and topological phenomena that's happening these days, but still magic angle twisted graphene structures are the only one where the superconductivity and the zero field quantum anomalous Hall effect are present in a single type of system. So if we ever want to couple such anomalous quantum Hall effect or some sort of zero field topological phase with the superconductivity, still this is the only platform that can provide that in a single material. So with that, I would like to thank my advisor, Pablo, great colleague, Yuan, as well as our collaborators at Harvard in Amir Yacobi's group, and all the funding agencies. And thank you guys for listening.